So yeah, we're going to talk about SIMD in complex algorithms, looking at standard library examples to help you understand how can you use SIMD in algorithms where you wouldn't think that it's possible to use SIMD. So yeah, hopefully at the end of the talk, you'll be able to apply SIMD to more complex things. So first of all, quickly about me. So Gabriel Mamis, I've worked a lot on open source on several projects like Keras, TensorFlow, Python. I have my own library, and nowadays I'm contributing to Mojo standard library. So what is a SIMD? So first, we have to understand what a SIMD is not to understand what a SIMD is. So how would you do, for example, to multiply multiple elements by 2 in an array? So let's say that you have the elements in memory and you want to multiply them by 2. So you're going to do a for loop and you're going to do a load operation on the first element, load it into the register, multiply it by 2, and then you do a store operation to put the result in memory. So you do the same for the second element, etc., for this third element and for the fourth element. So as you can see, you have a lot of load operation multiplied by 2 and store operations. So how would you do that with SIMD? Well, SIMD is a way to do this with multiple elements at once. So you issue one load operation, and then it takes all 4 elements at once, put them in the register, and then you can do a SIMD multiply by 2 operation, and it does this in a single cycle. And then you can do a store operation for all of the elements at once. So that makes it usually pretty fast. So why would you use SIMD in Mojo standard library or even in your code in general? Well, the thing is that SIMD is a way to get performance, and Mojo's focus is also performance. So this is not uncommon to get 2 to 10 times speedups when using SIMD compared to just a plain for loop. Also, you shouldn't be afraid to use SIMD because of compatibility, because most CPUs nowadays have SIMDs. So it shouldn't be an issue. You have auto-vectorization, which is something that you have to know about. Most compilers, when they see a for loop, they're going to try to apply SIMD to your for loop to transform your code. But that works in simple cases. But as soon as it becomes too complex, it doesn't work anymore. And you have to do it yourself. And finally, Mojo provides really, really good tools to work with SIMD. So first of all, you have the SIMD type with the parameters on the size and on the D type. And then you have var versus alias for compile time programming or runtime programming. So you can quickly differentiate the two. You have annotated assembly that you can use for profiling, and you can also have conditional compilation, which allows you to use different assembly instructions for each CPU.
Gabriel, just to add one point. So the reason there's a structural reason auto vectorization doesn't work very well. It's because when you want to do vectorization, you have to think about the data layout. And so C compilers, when they auto vectorize, are forced to use whatever data layout the C programmer used. And so, you can get lucky. Sometimes it works out, but really you're often very constrained that way. And so this is one of the reasons where bringing SIMD into Mojo enables or encourages Mojo programmers to actually think about data so that you get efficient access to the machine. But sorry, keep going.
Yeah, thanks for the tips. So what if the algorithm is too complex? So if it's a simple for loops, this is pretty straightforward to use SIMD on it. What if it becomes too complex and it doesn't seem obvious? So first, what you got to do is avoid hard to predict branches and avoid pointer dereferencing. What I'm meaning is like avoid load operations, avoid reading from memory. Then you can look at the standard library and see what SIMD functions are available and what you can use to your algorithm. Don't be afraid to use more instructions. Sometimes the SIMD version is going to be a lot longer. That shouldn't scare you. It's fine because you are processing more data at once. So most of the time it's fine. You can look at LVM intrinsics that provide functions that you might need or assembly instructions sometimes. If you're running out of ideas, you can look at the research papers on the subject. Really some algorithms that's really, really hard to find. For example, the UTF-8 validations, there is no way I could ever find this algorithm. So you have to do profiling too, to make sure that your code actually goes fast, otherwise it defeats the point. And also, it might be hard to make it work for any SIMD size. So what I would advise is first start with a fixed SIMD size, and then you parameterize it when it's working. So let's give it a shot with some examples so that you might understand how to use it in practice. So let's say that you want to make an algorithm with a SIMD that parses an integer that is in a string, and you know it's ASCII, and you want to parse it. So how would you go from the string to an integer with the SIMD? Well, often you have to use the fact that you have to understand your data and you have to understand how it works. So here, if we look at the ASCII table, for example, we know that in memory, the numbers written in ASCII for the digits for 0 to 9, they are contiguous. They are from 48 to 57. So what you can do when you have the byte value, you can take each byte and subtract 48 to it. So if you subtract 48 and then cast it to UN64, because otherwise you're going to run out of space, 8 bits is a bit too low for this. You end up with the digits that are in your string. Then you can multiply by the powers of 10. So this vector can be computed at compile time. So that's really important. You wouldn't want to do that at runtime. Then you end up with those values, and you can do a reduce add to end up with the final integer that you wanted to parse. So that's one way to parse an integer with very few instructions. If you're interested into just parsing numbers in general, so first you can look at the Mojo code. There is a implementation of atof in the pull request if you're interested. But also you have really good papers about parsing floats in general by Daniel Lemire and Mushak. That's really good, and I really advise you to read it. It also really provides really good information about just parsing number in general. That's really good info. Let's say, for example, let's take it up a notch and let's do something more complicated. Let's say that you have base 64, and in base 64 you have to read groups of 6 bits. When you read groups of 6 bits, it can be difficult because the group of 6 bits can be on a boundary between 2 bytes. And it can seem difficult because in the SIMD, most of the time you do operations element-wise. So that can be difficult to understand. How would you do that? How would you shift the values to put the groups of 6 bits in each byte? So we're going to see how we can do that here. So first you do a mask to take the first group of 6 bits. So that's pretty easy. And then you can do a bit shift by 2. That's pretty easy too. And you end up with the 8 bits that you were looking for. But then for the second group of 6 bits, that's a bit difficult. What you can do is mask. And then here comes the magic trick. So what you can do is you can do a bit cast. If you start doing a bit cast and working with UN 16 instead of UN 8, then you don't have this boundary anymore. And then you can do a rotate of the bits to shift them across the boundary. And then you have the pattern that you wanted. You have to use rotates because otherwise you end up with the issue with endianness if you do just a normal bit shift. So if you want to see how it works in practice, there is a pull request also for this, for the bis64 encode in the standard library. That's a really good read if you're interested to know like SIMD and Mojo, how that works. And also, if you're interested into base64, there is a really good paper by Modular and Lemire on base64 encoding and decoding, and it's pretty much at the speed of a memory copy, which is really impressive. And then you have like I think it's the most complicated algorithm I ever saw on with this SIMD. Validating UTF-8 length. We're going to do a really simple version of this, just because otherwise it wouldn't fit in the talk. Let's say that you want to validate UTF-8, which is a text format. Let's say that you want to validate it, and you know that it's a concatenation of one of those 4 patterns, right? You have those 4 patterns, and you know that you have every time a leading byte that tells you how many continuation bytes there is, and every continuation byte starts with 1 and 0. So for example, if you see this pattern, right, you see a byte that has 1, 1, 1, 0, you know that there is only 2 continuation bytes afterwards, not 3, not 1. And so you have to validate that. And that can seem really hard because they're in like random order, totally random order. They can be like across the SIMD vectors. It can seem really difficult. So we're going to see how we can do that in practice. So here, let's say that we have a sequence of UTF-8 bytes, but there is an issue in there. It starts with 1, 1, 1, 0, which means that we should have 2 continuation bytes, and we have actually 3. So let's see how we can detect this error with this SIMD. So what you can do first is do a bit shift by 4 of each element. You end up with all elements starting with 4 zeros, which means that all the values in the bytes are between 0 and 15. It is really important because actually there are a lot of CPUs that have SIMD operations to do lookup tables when you have 16 elements. And you have a SIMD table and you do table lookups, it's really fast. And then you can categorize those bytes that you have, which means that, for example, each leading byte has a value between 1 and 3, and it tells you how many bytes there is in the character. So for example, here you would have 1, and here you would have 3 bytes in the character. And this is, you see how now we can kind of detect it, right? You're supposed to have 3 bytes in the character, and you see that you have 3 zeros afterwards. So which means that you have 4 bytes in the character. Here is correct, you have 2, and then you have a 0 afterwards. So this group is 1 character. It's fine. We don't have the time to actually do the full algorithm and to how we go from this categorization to the actual Boolean vector telling you like if there is an error and where. But to give you a hint, you can do saturated subtractions and then bit shift, not bit shift, sorry, element shift. So you can, like, for example, you shift the full element by 1 and do a saturated subtraction of 1, and it would fill the zeros. I'll let you think about it, but that's the idea. So yeah, if you're interested in the Mojo code, that's a pretty complicated one. You can look at the pull requests where we make UTF-8 validation much faster. And there is actually a really good paper also by Kaiser and Lemery on the subject. And also, if you're interested into UTF-8, you can also read the paper because it has a really good introduction on UTF-8 in general and validation of UTF-8. So yeah, even if it doesn't seem vectorizable, maybe it is. Maybe it is. So I really advise you, if you're facing an issue with the performance in your algorithm, maybe at first glance it's not possible to use SIMD, but maybe you can. So yeah, try it. I'll give you some just ideas of what is possible so that you understand how we can tackle this complexity. So there are implementation of JSON parsing where you can do 9 gigabytes per second with SIMD. So really, it's a really complex algorithm. It's JSON parsing, and it can be done with SIMD. You have UTF-8 with UTF-16 transcoding. You have also base64 decoding that handles white space. It's really difficult because you have to like remove the white space to handle it, and that can seem really difficult. So yeah, SIMD algorithms are really underused today, mostly because like people relied on the compiler before, and they're hard to write. And with Mojo, it makes it pretty easy. So yeah, you can give it a try. So now it's feedback time for the modular staff about Mojo and what was easy and not easy with the SIMD. So first of all, really good the parameterizing on the SIMD size, on the D type and the size. That's really, really good. Makes it really easy to make portable algorithms. Profiling and updated assembly and debugging, that helps a lot, knowing what's going on. Providing high-level functions for working with the SIMD. Pretty cool, not having to meddle with the assembly or intrinsics. It's pretty easy to get things right. If it compiles, usually it works. It can be surprising, but usually it works. There is an easy distinction between compile time and runtime, so alias and var. It's pretty easy to do conditional compilation, and also if you come from Python, like me, it's really easy to port your NumPy skills to SIMD. It's pretty much the same API. So for the things that we could improve, I'm pretty sure we can improve that. First of all, the biggest pain point is that it's not possible to know what works at compile time and what doesn't. With those algorithms, you often have to generate SIMD vectors at compile time. And it's pretty annoying when you have to spend like 20 minutes writing a function and then you try to run it with an alias and it doesn't work. So that's a bummer.
So that should be a bug, not a feature. Is that because the LLVM intrinsics don't work, or is there a root cause for that?
I would say that pretty much all SIMD operations don't work at compile time. So like if you want to do a split, like you want to slice a vector, an SIMD vector, that doesn't work at compile time.
Can you ping me on Discord or something? And I'd love to learn more about that because that should be fixable.
So yeah, I'm pretty sure that pretty much everything that calls LLVM intrinsics, I'm pretty sure that doesn't work, but I'm not 100% sure.
All right, so again, I don't want to interrupt you, but please tell me about it.
Okay, sure. You have null terminated strings, so you might say skill issue. But I come from Python, sorry, skill issue. You have also LLVM intrinsics and inline assembly. That's not really well documented. That's a bummer too. Also functions working with only parameters. Sometimes you have functions that require arguments to be parameters, and when you read the assembly code, you're like, yeah, but that's not necessary, right? So that can seem a bit weird. Also, you have no bytes literal. That's just a bummer. It's just a syntax sugar. And you can access the benchmark module when compiling the standard library, which makes it not really useful for trying to improve the standard library. And also bitcast is a bit strange to use. So I come from Python. I'm not too used to it, but it seems weird to have to use pointer, address of, bitcasts, dereferencing. That seems really weird. It makes me think that there is like a load operation when there might not be. Anyway, so I'm pretty sure we can improve all of that. So really don't take it too bad. I'm pretty sure we can improve all of that. So many thanks for everyone that contributed to this work. Daniel Lemery for the papers and the inputs for the pull request and also the slides. Michael Kowalski for the neon variant of the table lookup. The table lookup, super useful when you work with the SIMD. Always keep it in the back of your mind. The standard library team for the code reviews, and the Modular staff from Mojo, because otherwise I wouldn't even do this. So thanks everyone, and if you have questions, feel free to ask. Yep.
Awesome presentation. Thank you so much.
Thanks.
I don't see any questions in the chat or in the Google Doc. Are there any live spur of the moment questions?
I have one. In Python, numbers are not really the system intrinsics. It's effectively big ints across the board. Does that complicate parsing in Mojo, or is Mojo using system intrinsics for the base numbers?
Oh, I can answer from standard library perspective because it's just an issue of standard library functions. I think we do manual parsing in the atoll, if I'm correct. But we don't use SIMD yet. Like those functions could be optimized. And since we output a UN64 int, just int in general, so 64 bits, we don't parse big ints yet.
Okay. Thank you.
There is a repo out there for working with big ints, so there's like a community repo, so yeah, we could potentially get that in the standard library at some point.
I just noticed Daniel joined. Welcome, Daniel. Gabriel was saying nice things about your work.
Thank you.
Yeah. It's nice actually that you're here because I have questions for you.
Okay. You can flip it around if there's time and ask him questions.
Maybe people from the Mojo staff can answer, but it's just, yeah, since you're the expert on this one. So I have a question about data alignment. So that can be pretty much an expert topic, but when I did all the algorithms project from your paper, I didn't care too much about data alignments, but I'm pretty sure that there is penalty if you don't respect it. Like, for example, if someone gives you a pointer to UTF-8 bytes, but it doesn't start at a correct power of 2, like let's say 64 chunk of data. So that can be, I don't know how much we have to care about that. I have no idea.
So in my experience, you don't have to care too much about it. It's always possible to sort of re-engineer the algorithm so that they're aligned, but it becomes fairly complicated. And in my experience, you gain relatively little, like maybe 10% or something like that. Because basically when you're, say for example, you have a block of memory and you're scanning it, you're going to touch every cache line anyhow, right? So you're not really saving, and there's no false sharing or anything complicated like that. So you have a small penalty that you can measure, like with AVX, for example. If you're perfectly aligned, there's a little bit of a boost because the load can be slightly faster when it doesn't cross a cage line. But we've done a lot of work on this topic, and we just basically do not care about alignment. And whenever someone tries to say, well, we should align, and then I reply, okay, let's measure. And very often the difference is very small. Now, it could matter, for example, if you're like engineering a C string length function where you want to find the first sentinel, the first null. Then people really micro optimize these things, but they write everything in assembly and everything, right? So in that case, then at that point, when you're at that point, the last like 10%, maybe it matters, but it does complicate the algorithms quite a bit because like UTF-8 is not naturally aligned on 64 bit 64 byte boundaries, so or whatever. So it's complicated, and of course also different systems have different gauge lines and so forth. So that's a little bit and SIMD length and so forth. So that gets a little bit complicated.
Thank you very much. I think when I read the implementation in Mojo of memcopy, I'm pretty sure we do like care about an alignment. I'm pretty sure we can we jump at the start to get to the middle.
That would be one algorithm where it matters. But most things are not memcopy, right?
Yeah, of course. So yeah, thank you for the answer. Are there any other questions? Because I have other questions.
We do have one question in the chat from Sawyer. Is there any story on adding reflection features that collections could use to do SOA type transformations, or is that going to stay as a regular MLIR pass for splitting things into groups amenable to SIMD?
I'm probably the least bad person to speak to that. I don't think we have any concrete plan at this point, but it's something that's interesting to look at. And so it's unclear to me when you so just to level set what SOA AOS means is if you have an array you have structs in an array, the transformation is make it so you have one array for every field of the struct. It's kind of like a database when you have a columnar store where you want to keep all the columns of these things next to each other. It's kind of similar to that. So I don't exactly know how that would work. We need, as you said, the ability to reflect over struct members and stuff like this. There's an engineer, Billy, I don't know if Billy's here, that's working on it. Yeah, Billy's here, working on adding some ability to reflect on traits in a more comp time way so that we can get, for example, downcasting. So you could say I have a trait of something that's any type, and I can now dynamic or comp time check to see is the thing I'm instantiated on actually conform to this other trait and stuff like this. So I think that'll come in, but I don't know if struct fields are there. Billy, do you want to comment at all? Or have you thought about
yes.
So
you're talking about basically type values and reflections, right?
Yeah, it's kind of the work you're doing is making it so you have the full trait conformance table available, but then this would be going the next step further and saying reflect on the structure of a type.
Oh,
And
yeah,
then
totally. Yeah.
and then somebody
Yeah,
would say like the full type AST almost.
Yeah, that's the goal. So we will eventually have all the struct fields, their types, that should all be encoded in the same way. So you can basically delve into the tree of the types.
Thank you.
So we'll see how it comes together. I don't know if there's a specific time frame on it, but this is one of the things that Mojo is really set up well to do. And so I think Billy's working on some of the fundamental work for that, which will be exciting for lots of reasons. It'll be useful in the standard library. And there's a bunch of other stuff going on as well. So sorry, Carolyn, go for it.
Gabriel, you have about 5 minutes left in your half of the slot today. If you wanted to ask Daniel any other questions, or if anyone else had questions for Gabriel.
Yeah. If nobody has questions, I have one. Yeah. So my question was about GPU. I've never programmed on GPU ever before, and I know that GPU is the next big feature for Mojo, and I wonder how that works with SIMD. Like, do GPU cores have its SIMD? How does that work?
Well, not really, right? So SIMD is really I mean, there might be exception, but it's mostly a CPU feature. What is generally true is that if you have an algorithm that you've designed with SIMD in mind, it's often a good starting point for a good GPU implementation, because you've made it more branchless. So one of the things that you notice with these algorithms is that there are very few branches, so they work in blocks of data, and they do their thing irrespective of, they're not very sensitive to the data inputs, and so it has that in common, and a lot of there's a lot of crossover, but and there are definitely tools that will allow you to make things a little bit more generic, that they'll produce SIMD or GPU implementation on demand. But in this case, the algorithms that you're talking about are really specific to SIMD, and they don't automatically port over to GPU. And I'm not sure that you'd want to transcode Unicode on GPU in general. That might not be the best use of your GPU also, but the crazy things that people do.
Thanks a lot. Yeah, that makes sense.
Any other questions for Gabriel, for Daniel, for anyone?
I do have more questions, but I'm not gonna like explode the time box.
You have 2 minutes left, so if it's a 2-minute question, go for it.
Okay. So I've only worked with Python before Mojo. So my question about SIMD is like, what are the pain points of using SIMD in other languages? Since I've never used other languages for SIMD, like just to have a better comparison of like other languages to work with SIMD versus Mojo.
Right. So when you work in like Swift, Rust, C, and even now C#, the latest version of C#, you basically have this approach with is equivalent to intrinsic functions, right? Which are basically mapped more or less directly to not always, but very often they're mapped to specific instructions. So it gives you like unreadable crap, but it works, right? So you have all these languages that do that. So in C++, so I'm thinking about projects like Chromium, Blink, the the Chrome engine and like WebKit, you know, Safari. What they do, they use like libraries that sort of abstract things away a little bit, so you don't need to have like different implementations for different instruction sets. So you have SIMD everywhere. I think Apple uses that in WebKit, and you've got Blink, Chromium. They use Google has its own thing called Highway, which abstracts things a little bit, and of course you can do your own abstraction on your own, which is something I've done for my own purposes, where you sort of abstract away, you know, the gritty details. You build your sort of own API, you know. So I have no idea. Well, I look at your code, so I don't know exactly how Mojo is going with this, but you know, but there are failure points. Like, for example, and I'll finish with that. Java is trying very hard with something like called Java Vector, and I think they're really struggling because they tried to abstract away, and there was an initiative also with JavaScript, and they sort of abstract away too far, and they get to a point where the code is really nice, but you have trouble getting the performance reliably. And so then you get into this weird point where you're writing SIMD code. It's very nice, but then very often it's not faster than regular code. So then it's a terrible place to be, because then you're better off not doing SIMD at all. So you have to balance things out, right? So if the code is really nice, but you don't have the performance, you're just wasting your time. So you don't want to go there.
Well, I think you're touching on like a really important thing, which is that people want everything to be magic and it just be portable. But SIMD, as an expert like you know, is like you actually have to know, or you benefit a lot by knowing on this chip there's this weird thing that you can do. And so one of the cool things about Mojo is I would say there's two major things. One is it's standardized. Like, so your point is like within C++, there's 52 different libraries. And so there's just like fragmentation across the entire industry, and that's just a mess, right? That's one huge advantage with Mojo is there's just one right way to do it, which is great. But the second is that the philosophy is don't try to solve problems you can't solve. Like, expose the power of the hardware, allow you to use the super weird stuff if you want to, but then also make it so you can write a conditional code and do that in a clean framework. Just to wrap things up, if y'all are interested in this, I'll nominate Evan here. He's writing a blog post about SIMD and Mojo, and perhaps more than one. And so it'd be really great if you could contact him offline, and maybe you can have a small group nerd out discussion too about this, because I think there's a lot the industry can learn as a whole.
Sure, thanks.
Love it. Thank you so much, Gabriel and Daniel and Chris and everyone. And let's hand it off to Maxim now, who's going to talk to us about hash functions and where to find them.
All right, thank you very much. I'm starting sharing my screen. Good, screen is shared, right? You can see it probably.
Yep, yeah, I can see it.
Super. Perfect. Okay, all right. So hash functions and where to find them. Right. First of all, what is a hash function? Well, basically, it's a function where we want to go from unbound data to bound data. Example is string to uint64. So it's not necessarily a reduction, because it could be that the string is actually empty or just a few characters, but we would like to get a number which is 8 bytes long. So it's basically just a projection, if you want, right? So what is it used for? There are multiple use cases. I picked 4. I think we cover kind of most interesting parts, where we say, okay, we have the data partition, we have digital signature, we have fingerprinting, and we have checksums. So checksums are verify data integrity. It's quite a technical thing, where it's normally used when the data is either stored or it's on the wire. And it might happen that because of some technical difficulties, the data was changed. So we have this checksum where we can just recompute and see if there was some kind of integrity issues with this. For this, the space that we need the hash in can be just 1 byte or 2 bytes or 4 bytes. This is not that critical at all. Fingerprinting examples are, for example, when we have Git commits or we have files. So we don't want to look into the whole file. We just have a function which would be able to represent something as a number, which might be here. It might be much more interesting to have like not just 8 bytes, but maybe 16 bytes, which should be wider, because like it's not a big deal if we have a collision. Actually, as far as I know, Git uses SHA-1, and nowadays it was proven that it could potentially have collisions, but it's still not a big problem because the was are very high, so it's not a big deal. A bigger deal is if we have so-called digital signatures where we want to verify the authenticity of the file. So if the file was tampered with, and not the same as with checksums. With checksums, we say we just want to see if there was a hardware error in a way. So there was no malicious intent to it. With digital signatures, we actually want to see that there was a malicious intent, and someone wouldn't be able to just recompute the hash after they tampered with the data. This goes into the direction of cryptographic hash functions, and those hash functions are mostly like 256-bit or 512 or even higher, depends on the how secure we want to have them. Right, and last but not least is for data partitioning. So basically here we think about grouping data, and here we have basically two use cases. We would like to have low collision, or a best case scenario, we have a perfect hash function. What is the perfect hash function? Say we have 256 data points, and this hash function, which actually produce hash value of 1 byte with no collisions. This is like the perfect hash function, but it's generally, in reality, it's impossible to do, but this is kind of a goal. But we also have sometimes a need for high collision. Locality sensitive hashing is the term that we think about, like in physical world. If you think about it, for example, zip codes are locality sensitive hashing. So if you have an address which translates to a zip code, you would like addresses which are close by to collision into one number. In the space of AI, we could think of actually word embedding as also as locality sensitive hashing, where we would like semantically equal words to be as close as possible in this vector space. No. Right. The simplest data partitioning function is just modulo, right? So like a modulo n is the simplest hash function in a way. The problem is a needs to be a positive number, right? If we have a string or multiple strings, we can build a mod from a string because it's unbound data. Why do we need a hash function in the standard library? Well, generally, we don't have to have it, but we would like to have an associative array, and there is a possibility to create an associative arrays based on 3 data structures with comparisons, but most of the time we would like to have a hash map, and for this, we need a hash function to translate keys into hash values, and then do grouping of hash on the hash values to put them in the buckets. But maybe we want more, actually. If we look at this Zig standard library, it actually has about 7 different hash function families, which are also used for checksums and so on and so forth. In Zig, for example, they like to re-implement lots of algorithms which also do checksums and so on and so forth. So it actually makes sense to, if you want to have everything in-house, to actually introduce multiple hash functions in the standard library for different use cases. Well, where do we find good hash functions, or rather, what is a good function at all, right? So like, because like goodness, it's a kind of a subjective thing. So good head function, we can say, okay, it is fast and it is high quality, right? What is high quality? Depends on the use case, right? So like, for example, where I talked about locality sensible hashing, we actually want this hash function to have lots of collisions. But if we talk about actually hash maps, then the high quality for hash map, and here's the definitions, it should ensure that two different keys are no more likely than random chance to produce the same hash value. And no matter what type of keys are used, the hash table is using the hash function should have its keys distributed randomly between the table cells. So here it's all about distribution, right? And it comes from this project called SM Hasher, and this definition comes from the distribution wiki page. Okay, what is an SM Hasher project? Well, generally, well, it's a little bit, currently there are actually already free versions of a project. This is why it's a little bit harder to talk about, but generally there was this user on GitHub who started it, where they collected different hash function implementation in C++ and did some testing on them. And I will talk about the testing in a few seconds. Then this repository got staled, and then the user Urban made a branch basically and fork and continued with the work. And I think since last year, user Wojciech on GitLab started a third version where they claim also to have a little bit better tests and continue with the work trying to like measure the best hash functions which are implemented in C++. All right, so if we'll look at the initial one, we have like this info where it's actually quite nice summary what it is. So it says some hash test function can be broken down into 4 classes. Sanity, does the hash function work, and does it do bad things with input? You'd be surprised, but actually lots of hash functions have UB or some other cases where it's actually not saying to use them, or it is saying to use them, but only on specific data, which is, for example, aligned to 64 bits or something like this, right? So, and it's not a good idea to use it as a general purpose one. Then we have performance. So here they actually measure how many cycles it takes to complete a hash and consume all the input. Then there is a point of differentials. Basically, the idea is that even a very small difference, maybe in 1 bit, should result in a very distinct hash value. This is due to the fact mainly for security concerns, because if someone can actually estimate what the result of the hash function will be, then they can start a denial of service attack by actually creating feeding your filling your hash function hash map with lots of collisions. And last but not least is basically the question of the key sets, to say like, okay, we have a bunch of key sets and we just may create hashes out of it, and we would like to see how spread out the values are. So basically, if you think about it, a good hash function is a kind of a pseudo-random function which can deterministically create a quite random result from your input data. Okay, so here we see like an example of SM hash test. This is from Ruben hosted project, and you see the hardware they use, and you can also like sort on the you have megabytes per second, cycles per hash, cycles per mesh, size, and quality problem. And you see that the first one, first four examples are actually just no-ops. So it's kind of like a baseline. What can we get if we actually do nothing with the data, right? We see here like a huge amount of megabytes per second. And then there is this one hash function, which is actually quite fast, right? And also in cycles per hash, it's great. But the problem is quality problems, insecure, zero, fails all tests. Basically, I will actually show this function later, and you will understand why it fails all tests and why it's insecure. But generally, it's a very fast hash function, which would work maybe nicely in your hash map, but it's like it's maybe not a good idea to use it. Here we see the Fletcher family. Fletcher family are actually checksum functions. You can also use them for hash map, and seems like they perform actually quite well. But again, UB and fails all tests. This one, rapid hash, is a new kid on the block. It basically was implemented this year, and it's a continuation of yhash. And it performs well. It has no quality problems, so it's generally it's great. Then we have another one, ahash. It was actually winner before rapid hash came along. It has one quality issue. It's written in Rust, so like basically, which is not a quality issue, but generally, like otherwise, it seems to perform well. Although, if you look at the megabytes per second, it seems like, for example, like rapid hash is faster, and then we have yhash over here. It's also faster than this one in this test, right? So like, okay, so those are kind of, if you are interested, you can go to a project and play around with the list and try to see like your favorite hash function and how it actually performs in this test. All right. I also created a repository where I ported a few hash functions. You can find it in this. It's called Mojo hash, basically, and I ported a hash. It takes like 101 lines, which is generally just not lines of code. It's just lines, including empty lines and imports and so on and so forth. So it's actually not that much like inside, right? So yhash is 98. I also implemented FNV1A, which is very simple algorithm. The 32-bit version and 64 takes only 23 lines. FX hash, it's a hash was used in Rust for some time, and it comes from Firefox actually, but now they switched to different hash functions actually. Then I re-implemented this O1 hash. I implemented MD5, and for reference, there is a standard library hash, which is DGBX33A, which is 271 lines, but it's actually the algorithm itself is very simple. Most of the stuff is just documentation and some like infrastructural things. So this one as well, if you are interested, please have a look. It's quite a simple implementation. As is. Okay, so to give you some feeling to how hash functions are actually implemented, and that it's not like a dark magic, here is an example of NV1A. 64-bit variant, where you see like we just define some constants, right? And then we just iterate over each byte. We load it, cast it to unit 64, then we kind of store it with hash, and then we say hash is multiplied by this other magic number. It's very simple, and this is how basically this algorithm works. So here we see that we go actually byte per byte, and we start to kind of store and multiply things. Here is the O1 hash. By the way, O1 hash function is implemented by the same person who implemented Y hash. And this is kind of like, I would say it was more of a joke for him, I think, but it's actually an interesting idea. What it implies is basically we do probing. We're not hashing the whole string. We just take the first, middle, and last 4 bytes, and we create a hash out of it. This is why, if you remember in the tests, like megabytes per second, it's almost like a no-op, because like we anyways will just take generally, 12 bytes and create a hash out of those 12 bytes. Fun fact, as far as I know, the NS string, which is like the standard string in Objective-C, had a similar implementation for a very, very long time, which is generally insecure, but very fast to actually build a hash out of any kind of string. Right.
Maxim, sorry to
Yeah.
interrupt.
Yeah.
I just want to make sure you have enough time for any questions that folks have. So if you want to take maybe a minute just to wrap up, and then because we're right at time, so I want to make sure you have a minute to answer questions
Okay,
too.
so I will just a second. I will then just try to run through fast. So basically, about what testing, I have like different text, and I wrote some benchmarks where I actually just split the text by spaces, and then I use those words as keys. And what I wanted to share, actually, like we have here the average compute times, and this is the standard hash. The times are a little bit slower, but the problem is the collision, the quality of the hash is actually not that great. We have different examples where you can see, like we have here just 20%, where here we are at like 370%. And corpus 7 is actually typical keys. I just took the action names of S3 and I used them as keys, because normally if we have keys in hash tables, we have like a longer descriptive names. Again, like time-wise, it's kind of okay, but like hash collision is not great. And last but not least, we have this file with just English words, which we can find on every Linux-based operation system. We have here over about 236K words, which have like min key is 1 character, mid is 9.5, and max is 28. And again, also here, it seems like actually here it's even it shows that generally the standard lib implementation currently it doesn't even utilize all the lower 9 bits, even though we have lots of input. So it actually should, but it seems like there is some kind of issue with the function. All right, so here.
Maxim, I'm sorry to cut you off. I think
I'm
that's
done
all
actually.
the time we have, but
this is this is
I'm sorry,
conclusion.
but if you, sorry, I was just gonna say, if you want to share the slide link, then we can make sure everybody has a chance to really check out all of your slides, because there's a lot of great content in there.
Yeah,
and sorry to interrupt you.
Sure. So do I have time for conclusion?
15 seconds.
15 seconds. Oh, okay. So generally, the connected library hash is not slow necessarily, but it has poor quality, which will reflect on the how many collisions we get in the hash map, and hence it would make would make the hash map look bad in a way, right? So what I would love to see is this approach where we have multiple hash functions, and one thing for wish list is unit 128 type, or at least multiplied full width on the unit 64 type. This is it from me then. I'm done. Sorry for taking too long.
No worries. Thank you so much. That was a great presentation. And if anyone has questions, if you can share them in the Discord server. Unfortunately, we don't have enough time for questions today. But let's real quick give a quick round of applause if you want to come off mute. Second.